Yeah, yeah, okay. So it's a pleasure. Yes. Yes, it's a pleasure to have Paola, Professor Paola Rodriguez de Hidalgo with us today. I'm going to make a little introduction about her career. She obtained her PhD in astronomy at the University of Florida, the US.
That is where we met
That's where we met, exactly.
many years ago.
Apparently it was, yes, too hot and too humid, maybe,
Yes.
maybe too close to Mar-a-Lago. But she moved to north to Penn State University, where she was a postdoctoral researcher for 3 years there. That was not north enough that you moved to.
You would never have done it. You would never have done that.
I would never have done. To York University and so the University of Toronto, where she was a postdoctoral fellow, visiting assistant professor, and research associate. And finally, she couldn't go up north because that was Canada already.
Good.
So she moved west to the west coast, and she was an assistant professor at Humboldt State University. And then finally, she moved even more extreme to Seattle, where she is now associate professor at physics and astronomy at the University of Washington. So whenever you want.
Thank you so much. It's a pleasure being here. I love Crete. It's my first time in Crete. I've been in Athens and Corfu before in a conference, but everybody's super nice. The food is so amazing, and I'm having such a great time. And I'm here until Monday included. I'm leaving Tuesday, so I would love to talk more. I love to have the seminar kind of in the middle of the visit, so that way we can talk more. I don't work in isolation. I love working with people, so I hope to establish some collaborations here. I have a list of some selected because I have many, many more, but I wanted to emphasize those that had the asterisk even more because those are students or previous students. Some of them now are advanced and postdocs and almost faculty by now, but are undergrads or students that I have worked as undergrad or grads, and I love that. I have some photos here, and most of my work is funded by NSF, by the National Science Foundation, and SDSS through the FAST program. Ask me anything if you want more about those things. Because the title is Quasars and Extremely High Velocity Outflows, I want to explain those things a little bit more. And I think that this department is very knowledgeable in AEN already, but maybe you haven't seen that many quasar spectra yet. And by the end of this talk, you're going to be experts. So what you didn't know before, you will learn it now. When we look at the sky, most of the things that we see there are stars, right? So if we take the spectrum, if we get the light from one of these dots and pass it through a prism, or because we are more technologically advanced, to some kind of a spectrograph that it will be more convoluted than the prism, we're going to get the typical black body radiation spectrum, right, that we have studied and we have seen many, many times. And these absorption lines, all of the dips there, are material that is in the photosphere of this star in most cases, and is absorbing some of the light from the star, right? But if we take the spectrum of this one, it will look maybe something like this, where originally they could not make up what this continuum was because it was no black body, but also all of these emission lines, they could not identify them. They did not match any of the wavelengths that we had on Earth if you have to match several lines at the same time. So at the same time, they also discovered that many of these cases had also jets in the radio. I know many of you here study more. So originally, these objects were called quasi-stellar, look like stars, but the spectrum is not a star, radio sources. And astronomers, you and me, we're very lazy, right? So in the 60s, having to type quasi-stellar radio source in a paper 20 million times was not good. So Hong Yu-Chu, a Chinese American in 1964, literally wrote in a paper, because the nature of these objects is entirely unknown, it is hard to prepare a short, appropriate nomenclature. So I'm gonna call them, for convenience, quasars. It was just the short of all this whole thing, right? Now we know that only 10% of them are actually active in radio loud, but the acronym stands with QSOs or quasars. Some years later, around the same time, in the 60s, we realized that if you reshift all of the lines, here, so you have the original spectrum Vega, if you reshift all of the lines by the same amount, you can identify then all the lines that, depending on the ratio, they will be more or more towards the optical, for example, this ultraviolet or not. Because of the discovery of this, Martin Smith got in the cover of Time. That, or I think this is because of the redshift, so the universe got much larger, or it was the 60s, there were all drugs, the acid trips, I don't know, one of the things, but definitely made it to the cover, right? And by now we know that the universe has expanded much more than what we knew then, right? And that these quasars belong to a zoo of other objects, right? That blazars, if you observe them then down the jet, quasars or Cipher-1 galaxies, the less luminous cousins of quasars, and then radio galaxies and Cipher-2, they're seeing them from this angle. And we think that, well, we know, I think it's well established by now, that the paradigm of AGN, of the active galactic nuclei, is a supermassive black hole in the center, surrounded by material that is in an accretion disk, and then a torus of neutral gas that beyond that. I don't need to, this is not a quasar, this is the galactic center group, but I love this video. So I show it every time that I have a chance, because measuring the black holes, the mass of black holes, to me still seems like magic. And I love it. The fact that these things are stars are moving around something that you don't see at the pace of planets sounds crazy to me still. And they have done several videos, so I have a couple of those ones, right? But in the case of AGN, you cannot measure it that well in many cases, but it has been established already that there's a relation between the quasars, the inner part, the supermassive black hole, and the galaxies around, from Ferrarese and Merrill in 2000, repeated many times, and I can find a paper every year to change this last one. And it explains the different types of measurements of the black holes. This will take in 2009, stellar dynamics, there's dynamic measures for the different types of galaxies. That's the one that I keep there. But I think that when I teach, I love teaching. I try to find even more didactic things, and I like this one when it shows that you have no black hole, the galaxy is it's very little, no massive at all. And in the very massive galaxies, you're gonna have the billion solar masses black holes, right? So there's a relation between the black hole and the galaxy. And these scales are completely different. So what we don't know is what is connecting the two scales. And that's why we started talking about feedback. There has to be something that from the inner region is talking to the outer region to either stop or quench or enhance the star formation of the galaxies, because there is a connection between the masses of the two, right? The possibility that I want to study today is that it's outflows, studying the most extreme ones, right? Material coming from the launch from the disk, with this obviously a representation, going towards the galaxy, bringing enough energy that's going to disrupt the galaxy and say, we're done with the star formation. Any questions so far? Speaking not too fast, my students always are like, chill a little bit if I'm going too fast, but I'm working on. So this is your first quasar spectral design, the one that I showed before, and we're going to focus on this region here because we're studying carbon-4, so carbon-3 then ionized. So you see the broad emission line that I showed before, right? That is created in the broad line region. We have the absorption lines that we saw before as well, right? So it will be all of the dips that are going down. We know that the ones that are on top of emission lines are exactly the same ions, so carbon-4, silicon-4, nitrogen-5. But then, starting already in the 70s, 80s, they start discovering these broad emission lines, the BAL quasars that are very broad. Again, we're not very creative with names, and also going very fast. This one here has a maximum, the center speed will be around 10,000 kilometers per second, so 0.03 decibel of light. In the 90s, my PhD advisor discovered this case, observing a lake where there was some absorption there. And if you think that this absorption is the silicon-4 or the oxygen-4 that has been blue shifted, silicon-4, then you're expecting carbon-4 at the same speed in this region here, right? But we don't have anything. So what he proposed at the time is that this could be carbon-4 that is outflowing really fast. So when you see the blue shift from the carbon-4 all the way there, it has to be 51,000 kilometers per second. But we need to confirm this, because when you only have one broad absorption that you don't see the doublet, you cannot identify, it doesn't have the name, right? So you need to know what this is. So we have called them extremely, because people were calling this one's high velocity. Maybe I have spent too much time in the US by then, too much MTV But that's why I decided to go extremely because so it's the energy of the United States exciting. For the talk, I'm gonna put these two lines all the time. The one here will mark the 10% the speed of light, and the one here will mark the 20% the speed of light. So even if you don't identify well the emission lines that I'm gonna try to label all the time, you can find this is the region where we're searching for the extremely high velocity outflows because it passed the 10% the speed of light. So the way to identify if that is correct is carbon-4 is that when you observe carbon-4 at the same ionization, more or less, you will can find nitrogen-5 and oxygen-6. So they will, if they are in the same outflow, they're going at the same speed, which means they will be reshaped to the same amount. The problem here is that if you have a nearby quasar, your Lyman alpha forest is very weak. But if you have a distant quasar, your Lyman alpha forest gets more and more complicated, right? We know that the Lyman alpha forest, this is a video by Andrew Ponten that I love. It's just going through all of the gas of the universe that is mostly hydrogen. That when you have a galaxy, you're going just by a galaxy, it's going to create a dump Lyman alpha there and more absorption lines. So the farther you are, the more you're going through universe, the more Lyman alpha forest you're going to have, right? So during my PhD, my advisor said, we're going to get HST data and we're going to search for nitrogen-5 and oxygen-6, and we found it. It wasn't easy. I don't love working on the Lyman alpha. There are way too many lines, but we clearly could see two dips that match exactly the speed. We can match the doublets and so on. And we could not detect any other ions, but at least we could confirm that this was going at 51,000 kilometers per second, so 0.17 the speed of light. The other thing that you can observe here is that the oxygen-6, the doublet actually was resolved. You could see the doublet, and the oxygen-6 doublet, the optical depths, that measures the amount of absorption in a way, it has a ratio of 2:1. You should see the blue line, not 2 times deeper because it's optical depth, so not exactly, but close. And it's not. They're actually very close. This actually can happen, and it's a way to know that this gas is relatively close to the black hole. If you assume that this is your source, so this is going to be the accretion disk behind that is emitting in that wavelength, and then you block part of that, but never the whole thing. Because imagine that you have this thing here, and I make this incredibly saturated. I might add in material and add in material and add in material, but you're never going to reach zero flux because there's always 20% of the flux that is reaching you. So this coverage fraction actually allows us to get better estimates of the optical depth because that's the generic problem, but we can actually do it. We got a coverage fraction of 0.8 or 80%. And with that and some cloudy analysis, we're able to get the column density, the ionization, and the numbers were relatively small for other BL quasars, but the velocity was going really fast. I want to see the importance of that in a second, right? Notice that the mass outflow rate goes with the speed, but the kinetic luminosity, the energy goes with the speed to the cube. So why is that important? Because this is how we measure the amount of feedback that might be reaching to the galaxy, right? The mass and the energy. And if we compare cases here that had speeds of 0.2 versus the speeds of 0.03 that I showed at the beginning, that people were studying massively because of this v to the cube, just this change of a speed is going to make your kinetic luminosity, assuming that all of the parameters are the same, 300 times larger. So we're talking 2 orders of magnitude larger feedback. With these cases that barely people were just studying and we had a handful of them.
So what do you assume about the outflow? It is 4 pi for the full sky.
Exactly. So all of those numbers are here, right? So that one will be there. That we yeah. Exactly. Well, we assume it's actually relatively thin. So for these ones, we assume the same numbers as the BL quasars, but in each paper where we say if this is slightly smaller, this will be the number. So this 300 times is assuming that all of the things are the same, but it's true that the distance could be different. That could be different as well. So you have exactly. Yeah. Yeah. Just the number. Exactly. And exactly. So the incentive of if all of the things are the same, but that means that we need to know the distance. We need to find it. Yeah, we need to find the distance, and I'm going to show you how we find it. And we also need to know this. And for that, we need to know how many times we observe them, right? Because if you assume that you're seeing them in random lines of sight, the number of them will tell you a possibility is also that they can change and evolve in time, but it will tell you something about how many times you're actually catching them in your line of sight.
But what I'm saying is that if it goes over the sky, how can you see the accretion disk? It should be covered.
No, if it's close. These distances are really close.
It covers the whole sky on its own.
Oh,
thing.
sure, no,
You should not see
sure,
the
sure, sure.
this.
No, I'm gonna show you. In the launch, in all of the simulations of launch, the accretion disk that we find in AGN, it gets launched out of the disk and then it gets pushed by the
So
radiation.
you should
So
not
it's
see
never
it.
a sphere.
So you should never see the disk. That's what I'm saying. There is no line of sight if you see the accretion disk.
No, you do. I can show you a couple of things, but yeah, let's go on. I'll let you on and then I'll show you how to do that. So hopefully I have convinced you that I'm gonna try to show why we care about these things. One, that there are potential feedback mechanism, but also that it's extremely energetic, or those things are actually connected. But also the fact that we're missing outflows. And as I was saying, the frequency of how many times you actually observe them, depending on the line of sight, tells you how many are there. And we need to compute how many times these things are actually observed. And people that were studying this region with certain, and maybe you have heard about bandicity index and absorption index. These are like ways of, in large samples, find how much absorption you have there that is integrating all of the absorption from here to here, more or less. If you measure it here, it will be 0 because the integral starts here and there. So you will have no absorption. It will be very small. There's no broad, there's not deep enough. So you have to move to things here in order not to miss outflows. So we need to expand this definition. So this is something that for EHBOs we now have done. But also to test as extreme conditions, and I'm gonna show some simulations that hopefully are here. So if you have the disk here, these are simulations by Daniel Proga in University of Nevada, Las Vegas. What we did here is look at different lines of sight of those simulations and reproduce the absorption that we have. Let me start from the beginning again. And if you look through this part, you're going through so much gas that you will have this broad absorption line quasars that people will be seeing at low velocity. And then just in a very thin layer here, you can actually start seeing things that are detached for a little bit, but not too long. They're actually very variable. But we were not able to reproduce something that is sustainable there at the speed of 30,000 kilometers per second. And we haven't done it yet. This was, to say this every time, more than 10 years ago. It's been a long way. But even more recently, thanks to Sirocco, Sirocco is a radiative transfer, a Monte Carlo radiative transfer. I don't use it. It was called, unfortunately, originally Python. I think it was Lon and I don't remember the other, Nike, I think, in 2002. And later they have changed it to Sirocco, but they were not gonna fight the Python other name because it was much stronger. So they have changed to Sirocco here. And again, we can create a spectra. We have these radiative launch winds there, and we are never able to find enough detachment. This is the silicon 4 that goes with a carbon 4, but the carbon 4 is not going very fast. When we actually have maps where the carbon 4 shows enough abundance to actually create absorption. So we'll keep on playing and we're giving them more information from the properties that I'm going to show in a second, but we needed more cases to find those properties. Because remember that originally, there were like 5 cases in the literature, and they are relatively easy to find. You probably have heard about ultra-fast outflows, UFOs. I hate acronyms in general, but this one actually really pisses me off because I hate to put a grant and say that I'm gonna study UFOs. But the UFOs are actually detected in X-rays, and some cases are incredibly convincing, definitely. You know, there are rigs and pump, but this is right by Tom Bessie, by the way. But other cases are pretty okay, still the last errors. And some of the cases in the papers themselves, they put like, is this an outflow? Because the absorption is so weak, right? And it's very difficult to detect in X-rays, as you probably, many of you know. Well, in optical, because this has been reshifted enough to put it in the optical, with SDSS, it's much easier to detect the EHBOs, which might be the same phenomena that UFOs or not. To search for that, we need to place them in the optical in the range of SDSS. So we need emission ratios that are more than 1.9. And we study the brightest quasars because you don't want to search for absorption on something that is incredibly noisy, because then you don't have a good confirmation that you have detected an EHBO. So we put a signal to noise more than 10. So when we have more than 750,000 quasar spectra, you can actually do this restriction, right? So again, a video that I don't need to show, but I think this is also like amazing and magic. So I don't study images, but SDSS have taken images of the galaxies, knows the registers of the galaxies, which means that you can actually find this strip through the universe, looking at the galaxies on your left and your right. Again, I use a spectra, so it's not this, but to me, the fact that Again, 750,000 quasar spectra plus everything that you have this is to me is kind of magic. But we'll go back to the spectra. For DR9, for the data release 9, I downloaded almost 7,000 spectra. We have published that in 2020. And for DR16, we downloaded more than 21,000, and we did some projections that I explained in the paper that we're preparing at the moment. And I work with a lot of people, as I said, and mostly undergraduate students. University of Washington, Bothell campus, the campus that I am, is an undergraduate research institution. So I do a lot of research with undergrads, and most of my research is done by them, obviously with me in the training. In the 2020, we did an algorithm to normalize the quasar spectra, because in order to find absorption, you have to normalize it first. But then Michael Charles here in the DR16 improved the algorithm, including some test regions to see the power law was going through where it should go through. But also that test allow us to measure absorption right away in the normalization. But if not, when it was normalized, and in the case it was not to, and Wendy start running this to the other codes that we have that detect any blood absorption for more than 2,000 kilometers per second and broad enough more than 0.9 the flags to see if there's any detections here. Again, remember that if you find this and it's silicon 4, you have to have carbon 4 absorption at the same speed. This is what the gray represents. But if you don't have anything, it means that, for example, in this case, we have absorption that goes with that, absorption that goes with us. These two are not an EHBO, but this one is, because there's no absorption there where the carbon 4 should be if that was silicon 4. So doing that and being very picky, that whenever there was a possibility that there was absorption there and it was not sure, we will reject it. We include it as a candidate. We calculated in the case that we have the Badin's index, the Pmax, the velocity max, the minimum, the equivalent net, the depth, and found in the first sample 40 EHB quasars, and in the second sample 98, which means that originally there were 5 in the literature, and we multiplied by 20 just by using these large samples, right? These are examples of them. And again, this is not like the UFOs. There's no doubt that that is absorption. And then you have nitrogen 5 and oxygen 6 exactly at the same speed. That confirms the speed and the nature of that outflow. And again, I'm using the 2 lines for mark. In this case, the velocity, the maximum velocity is 0.14, the speed of light. But we have many more cases. So I have this one here that has the nitrogen 5 as well. We find that nitrogen 5 is present when covered, when you have the range of wavelength covered, and typically is stronger than carbon 4. So we're giving data for the simulations that they need to find as well and reproduce. And that oxygen 6 also is present when it's covered, but it's harder because it's much in the blue line, and then we always have in the blue region, and we always end the spectrum there, right? This is similar to what I have studied in other cases. Then we have this one I also love. The nitrogen 5 shape is very similar to the carbon 4 shape. And then this one that it was meh, like there's nothing else, the shape, but it was the fastest of the bunch. So at the time, a graduate student, Jesse Rogerson, that is a fantastic outreach speaker, included this in a talk and calculated what would be in the speed in hurricane categories. And when he did that, we published that in your category 77 hurricane. And this stupid one that is the most stupid of the bunch caught the eye of a lot of the news, and it's there are videos. Again, it made me realize how media doesn't mean the most interesting thing from the science perspective, just whatever catches the public. But if the public learns about these things, so be it. With this, again, we have a total of 138. Now we have enough numbers to give statistics, to start looking for the properties. Is there something particular of the quasars that host these outflows that is telling us something special? So one of my students, that is still my student, Anna Ricci, calculated, grabbed the ranking 2020 data. We started collaborating with her, and that had the Eddington ratio, the volumetric luminosity, and the black hole mass, and placed these things in plant where you have the original. Here's the parent sample there, and in the histograms is the blue, and the EHBOs of both samples together are the red or the dots. And I'm including here the carbon 4 blue sheet, but I'm going to talk that in a second, so I'm going to skip it for now. So the things that you can find here. If you look at the dots relative to the parent sample, they're clearly, all of them have larger Eddington ratios. They are in the larger Eddington ratio part of the population, and you could see that also in the histogram because it displays relative to the parent sample, right? So we need to have larger Eddington ratios. That makes sense to me. Also, you don't find EHBOs in this part of the volumetric luminosity black hole mass space, parameter space. And how I read this is that for each luminosity, there is a maximum black hole mass beyond which you cannot find an EHBO. And that to me also makes sense, because if you are launching this from the disk, if you have to have luminosity to push it out. But if you have a supermassive black hole that is too massive, it might bring it back, which means it will be a fail wind and you will not observe it. So this actually, in a way, is confirming, no, but like strengthening the case that these are launched, these winds. We observe them in very luminous quasars, right? So obviously we don't see them in these ones here, but just by chance, besides doing the systematic studies, sometimes we find cases in the literature as well. So I think it was Wolf in 2018 that published the original spectrum of this. Is already used by my student, one of my students, Liliana Flores, where we said this has an EHBO. It has a very broad carbon-4, but in this case, this was blended with silicon-4, because if you observe here, we have carbon-4 at lower speed. So if we look at the speed here of the silicon-4, is a blend of carbon-4 and silicon-4. So you could just not measure this and say, all of this is the mass of carbon-4. We need actually to do a little bit more work. So what we did, and by we, I mean Liliana, with my help, because it was mostly her and she did a beautiful work. This is the result of her feeding of that region. When you can see that these broad doublets, the three of them, the blue, red, and doublet, are the carbon-4 EHBO. And then these narrow lines are the doublets of silicon-4 that we can match beautifully and perfectly. We did this in combination of studying the carbon-4 region at low velocity with the silicon-4, go back and forth iteratively. And then we created that. With that, we passed that data to Justina Vietri in Milan, that it was leading this paper. And we calculated a column density in the ultraviolet around 20.65 in one large. But they also have X-ray data. And in that case, it goes to the 10 to the 23. And we're finalizing this paper. She wanted me to send the final comments yesterday, but yesterday was a holiday. So we went to the beach and to Hania, which is beautiful. So I'll do it tomorrow. Liliana also is doing another study thanks to, she obtained a Mary Gates, one of the most prestigious scholarships for students at UW. It is the mother of Bill Gates. So they are giving money to have their name in this kind of things. So if I put the lines there, there's not absorption there in the region that we studied from the 10% to the 20% speed of light, right? But you can already see that there's a strong absorption there, right? So what we did is like, okay, we're gonna adapt all of our tools. Instead of analyze the things in this region, let's move forward and study the region there. So when we do it, you can see that the maximum speed is more than 90,000 kilometers per second. So we're talking about now we're going 0.3, the speed of light is in the Lyman alpha forest. And I have promised I will never study that again after my PhD. So I got the student doing it, but I help her as well. So all of the great things are things that you have to mask because it's, again, a lot of Lyman alpha lines, a lot of hydrogen, right? But she has the combined fit in purple that is beautiful. She has two pairs of Gaussians, and again, all of the mass regions. And we're passing all of that data to Patrick Hall in Toronto and more to finish that paper. So she did that part of the calculation. The blue shift that I said I was going to mention later. In the R9 already, Amy Rankin and I decided, okay, we see that these things have a lot of energy and high speed, very extremely high speeds in the absorption. Do they also show emission outflows that it will be easier to detect if we wanted to see in other cases? So she had already studied many times the parameter space of the carbon-4 emission line. In this case, both of the things are emission, the equivalent width of the line and the blue shift. And she had noticed that in the case of comparing the non-BL quasars to the BALs, there were not big differences. A slightly different the part here for the blue shift, but actually the histogram of the equivalent width is incredibly similar. So what we did for this paper is as simple as say, okay, we're gonna calculate the same parameters for the EHBOs and place them in that map. And you can see for the EHBOs, there's already a larger, for the histogram here, when you look at the dots, when the population here is much smaller, with a statistical analysis in many different ways, because obviously the numbers are still much smaller in the case of the EHBOs. but clearly there was no way that finding this was random picking numbers just because you have small numbers. So clearly there are more outflows and emission at the same time than absorption. One of my students, Abby1, repeated this experiment, which is now even much stronger. Like now we have better numbers, the statistics got even better. Doing it again now for VR16, combining VR9 and VR16. We're gonna have, hopefully publish this soon, but Abby just got an amazing job at Microsoft a couple of weeks ago. So now I need to get her to finish this paper, and that's not gonna be that easy. That's the only problem of working with undergrads. You have very short time sometimes. The case here that in this parameter space is not special at all. It's neither the weakest, the strongest. It's kind of in the middle of all of them. Is one of the cases that already in the 2020 paper, we have noticed that it had a lot of absorption. It was one of the strongest absorption profiles that we had, right? So thanks to a grant of NSF that allow us to investigate the most interesting cases, together with Joseph Choi, who was in Oklahoma, then Montreal, and is moving to Michigan soon. We look at the spectra of this case when we actually found several cases. We put the composite here, and we start measuring all of the absorption there. That is variable, and we have now both absorption at high velocity, but also at low velocity in the case of the DR5. And first, we detected many things. Again, in this case, we have done more carefully, not more careful, like more in detail. It's one of the particular cases that we study with a paper by itself. So first of all, the emission lines remain remarkably similar. What we do is a scaling down, but we don't change anything else at the scaling, and you can see that I thought that these were wiggles of the noise, and I don't think that anymore because it actually matches very, very well. We also observe that when you have here the silicon-4 emission line with oxygen 6, and this dip here, this actually is a dip of carbon-2 emission that you can see in the absorption. So the absorption has to be so close that it's kind of in the same region than the emission, or the absorption is very patchy that you can see the emission as well, one of the two, because you don't absorb the emission. You absorb the continuum, but not the emission lines. So with the silicon-4, it goes down, it brings it down, but you can see that the shape actually remains the same, and we use the same template there for both, right? And what we did in this paper is that Joseph Choi is an expert on symbol modeling. I don't know if you're familiar with that. It's something that Karen Laley developed in Oklahoma. There is a state-of-the-art novel spectral synthesis code that does forward modeling, things that I don't know if I can explain to detail, but ask the questions if you have any, which is using grids of ionic column densities. And it does like velocities, I think you say it better. It does it by each velocities and trying to study all of the absorption at the same time, but also fits the continuum emission and absorption at the same time. So this is the continuum fitting the emission and the absorption all together. So you create grids, do all of the ions at the same time, and then you get parameters. Still, because this is novel, it's I think well established, but still, the first paper is 2018, and some people still had some questions about if it's doing things perfectly, which I think it is, but we wanted to be conservative. So I use the typical apparent optical depth model that everybody does that established, it's well established that it creates lower limits for a lot of these things, but not best estimates. So that's why the lower limits you have there, and with the distance with different parameters there, and we also did it in symbol. So when you compare one to the other one, in symbol we went 21 to the 8 in the logarithm of the column density. Here we have more than 21.2, 21.3, which means it matches, again, lower limit, best estimate, so we get that column density that is much larger, an order of magnitude to what we found in the other case, for example, right? So when we look at these cases and we study the distance, and I can explain that later if you have more questions about that, we get estimates of the distance that it could be, where it could be, if it's the closest thing, or what is the farthest one. So these are the numbers that correspond to that. But look, even in the smallest case, you're getting 70 or 50, right? Solar masses, the rate of the mass outflow, right? And in the case of the kinetic luminosity, ranges of 46 point something to 47 point something for both of the outflows. So it's a lot of energy, a lot of mass that is going towards the galaxy. How long it's traveling, how far it's reaching is something that I would like to study oxygen 3. So that's why we're talking to Tanya to put a grant about that, proposal about that. In the case 138 cases look like a very large number. However, if you look at all of the cases that we studied, 6,000 and 80,000 and so on, it's less than 0.1%. So you could say, well, no, this is a rarity. It barely happens. Cool. But what's the problem? What's the deal? Well, I wanted to study then the evolution of these things. This is a range that we have to use because SDSS forces us to do that, but let's go in the other directions. So what happens if we go less than 1.9 and more than 4.5? Well, the 1.9, I haven't published anything yet, but a student, when I was in Toronto, so we're talking now about 10 years ago, did a preliminary study of the time where she downloaded a lot of Hubble Space Telescope archival data, because obviously for this you need ultraviolet in the observatory. Originally out of them, but when you start removing things that had their own redshift, that had no redshift available, that didn't have the right spectral coverage, that was the killer, that there was no public data large errors, and things that were, these are the ones that we were able to study, so only these 27. But how many of them we found EHBOs? None. I want to repeat this now again, so I'm putting an SFAG grant this November to complete this now that HST has created this legacy archive. So it's not as convoluted as it was originally. It will be much easier to download these things. And then an undergrad with all of the tools that we have, we'll be able to do it again. So I will be able to update you if this number remains close to 0 in the near future, hopefully. But for now, I'm going to put 0 in the one case that it was the very first observed of an EHBO. What happens at the larger, at the 4.5, and this is when things get very interesting. Already from our studies, we have noticed that there was a shift. If you compare the parent sample to the BL quasars in blue to the EHBOs in red, you can see that if you're looking at how many cases you have at this redshift, in the red, they seem to be more cases towards the largest cases. If you normalize the number relative to the parent, we always had 1. This is just 1 because it's 1 case. 1 out of 1 in that bin that had a large redshift. So it was like more here and that. We repeated this for the R16. Again, one of the latest bins have 1, that, and slightly less, but still, maybe there are more cases at large redshift than no. But we had to end there because SDSS, even when you will find some cases that have original redshift 6 or 5.5 or something, we realized that all of them were misidentifications, unfortunately, when they think this carbon 4 is H beta. So 0 of them were actually useful. But more recently, in 2022, Biscetti published a study with SQR30, the Shooter Legacy Survey of Quasars, with cases between 5.8 and 6.6. That paper made it to Nature, Nature, I think. And here they published that in the case of the USQR code, they find something similar. In the 2022, they published this already. This is for the 2023 paper. Where you can compare that to that, they already have the cutoff for the high redshift cases comparing to the SDSS cases. They also find that only in this part of the parameter space, but in the case of the EHBOs, we actually find them also in that part. We also have to compare numbers and put it all the same, right? Then this student, Anna, besides doing that, decided, okay, now let's grab the ESQR 30 cases and put them in the plot with the SDSS, but now let's label the ones that are EHBOs with the stars to see if the stars are in a particular part of the parameter space, the same way that in the previous case, they were already high, large Eddington ratios compared to the rest of the sample. And what we find is that no, in the case of Mazzucchelli, it's the 30 plus and a couple of other cases that they added. That's a star, that's a star, that's a star, that's a star, and that's a star. We found 5 cases, but they're all over the range. So we will find that they were the largest Eddington ratios, a high redshift, that ends to be the case. And then we're working with them now to expand this things. So, however, it's true that it's still low statistics, and we are finding obviously the most luminous things are high redshift so far, because that's how you do it. 5 out of 30 something is more than 10% of the cases. So we found 0 at low redshift, 0.1 in the case of SDSS, but obviously we have large numbers, and we were very conservative, like eliminated anything that could be something else. And then in the case of this redshift, it's already at 10%. And I got greedy a couple of summers ago, and I said, what happens at redshift 7 or more? And there are only 9 quasar spectra so far in the literature. Sarah Bosman compiles a list of all of them. So that's something I got my students to just look for the papers. It was a literature study. There are 9 cases, go for the papers, get the spectra. obviously the images of the spectra because they don't show the spectra there. One case had already an EHBO. They actually had labeled it there. One, another of the one also had a very strong EHBO. Again, this is the 30,000 kilometers per second. So we have 9 total, and we're already in the count of 2 for sure. This one here is something that Jan, the Ponyhuella 7.5. I think it's very weak. We need the spectrum to actually be able to study this better, but I think it might be there. I'm saying 2 for sure, 3 maybe. This is the case that Bañados, in fact, I worked with Eduardo and with Onowe at the time. We don't think so, but maybe. This is the one of the maybes, maybe. And then this one is Matsuoka, 2019. The spectrum is incredibly noisy there. But if you look at that in La Region Guerrera, I have put the 2 lines again for the 20% the speed of light and 10% the speed of light. There's clearly absorption there, but we will need to study. We will need to study it more carefully to be able to tell, right? But let's say that 2 for sure out of 9, 3, 5 maybe. So we're talking about getting close to the 50% of quasars that have EHBOs. That is something that we barely knew and barely care about some time ago when we're going. So clearly there is evolution of this beast when you study that. And soon with James Webb Space Telescope, we probably will have more spectra to be able to tell if this is real and find more cases and then be able to calculate all the parameters of feedback and so on. I have 5 minutes, but I want to leave them for questions. People are going to leave around 2, right? So I can show you studies of variability if you have questions about it. I'm going to skip them here quickly because I have shown already some variability there of some cases, but I can talk about variability more if you wanted. But I wanted to finish by emphasizing again that all of this work has been done to get me together with undergrad students that I think that can do amazing things. That is why maybe I joined a couple of years the NSF Physics RU Leadership Group. This is an acronym that has 2 acronyms in its acronym. So I hear acronyms already, but this is like a big one. And I became the chair. I left last year because I've been on sabbatical now. And I know that it's very difficult sometimes for students, if you have a students undergrads that want to do research experience for undergrads in the United States, with the current climate, political climate is going to be even harder, but we can try to make it using federal grants. If you have students that want to go there for a summer, talk to me. And this is the whole summary of everything we have talked. I will leave it there later, but we can go through that more. But I prefer to show images because I think we are more visual people in general, and leave it some time for questions and say thank you for listening. And I'm looking forward to all of the questions now or the next days I'm here.
So, very
Thanks.
Can you measure what fraction of quasars at a given Eddington fraction produces Roche absorption lines? First, and whether this fraction is consistent as a function of redshift.
So for broad absorption line quasars that have larger numbers, because even when I have normalized a lot of these histograms here, and I can go to those ones there, they are normalized. We have enough numbers to do that. But for the EHBOs, though, the numbers are still very small. So if you try to now then bin them in another parameter, it's really hard. But again, we're already in 100 something. So that's something that we can study in the future with more numbers, hopefully. What do you think that we will find if we just look at a particular?
Yeah, I'm just wondering because this has to do with calculation list.
Yeah.
And the thing is that when you count up the end dot,
Yeah.
then you start plotting wings.
Yeah.
So one would expect that the driving factor would be the end dot, the Eddington fraction. And this was in the higher the Eddington fraction, the more the stronger the occurrence of the very fast outflows.
Yeah.
And comparing this fraction with this fraction can give information about the covering factor.
So let me show you this one here. I guess this is again, the EHBOs will be the dots here. So if I look at where they are within the whole parameter space, they're clearly at the large Eddington ratio, right? But if I'm looking at only one Eddington ratio oh, there I have very small numbers still. But with SDSS5, for example, now I'm part of SDSS5, we hopefully were able to expand it. So that's the problem.
Yeah, because then you can make the connection with Astrophysics.
Exactly.
You can start getting information about the
Exactly. Yeah. And we're giving these things. One of the things that using Sirocco now is that they can change the parameters, right? So you can change the black hole mass, you can change the Hinton ratio and see we're observing more things. What we seem to have been having the problem is that whenever we observe the absorption, is all the way to 0. So, so it launches and then it gets pushed. So then you have it at 0 and then at all the speeds. But we're not able to find the cases that are detached, that we only observe with absorption past 30,000, but not absorption below. Yeah, but I wonder if we crank the Hinton ratio, we'll be able to get that. They are doing grids of simulations. It takes some time. Awesome. Thank you.
Okay, yeah.
Any questions? Thank you very much for the sign. Let's just have a question about the evolution of the equation.
Yes.
Okay, all the statistics is very low.
Yeah.
Let's assume that these numbers are whatever. Would we expect interpret these results in terms of
Exactly. Great question. I think that obviously one of the problems is that we know that we already knew from this study that we observe it in the case that are less luminous, right? In the more luminous. That's why a low redshift, because they have lower luminosity, I was not expecting them in the first place. So the touch, removing or detaching the what is it because it's luminous, it's a high redshift, or it's high redshift, it's luminous, it's hard unless you have very large numbers, that you have the whole volume to be able to tell, right? So the problem is that that's not happening here yet. So obviously we're seeing the most luminous. So that's why we're seeing the evolution. I though, however, think that because we see more luminous things at high redshift, it's an intrinsic evolution, not only the case that what we are detecting, so it's a bias, right? So what I think is that this might be a phase and relates to one of the questions I was asked before, right? If this is a very small thing, it might be that it's a very thin here, just happens in a very narrow line of sight, which means that it's happening, but in order to detect it, you have to go through a line of sight exactly. But the coverage, the covering fraction of this gas, it might be doing more in bursts, which means that you're observing and it doesn't matter which line of sight you're actually looking at. So I actually think that is affecting, that is way more gas, the covering fraction, the amount of things in the sky will be much larger, which means they are more easy to detect. So I think that actually has some meaning.
the same question about the interpretation
Yeah.
of the evolution?
Yeah, so yeah, no, I'm very excited. I'm hopefully going to Italy to work with Sketty. She was applying for jobs, which I was in shock that she did not get a job already with a nature paper right away. And Justina next month, hopefully, to work about that.
How is geometrical effects?
Yeah.
and so on, if this persists,
Yeah.
right, then would it also imply that since you have much higher emission rates?
Yeah.
And this has implications about the seeds that you
Yeah,
need.
exactly. More violent universe in the high redshift, more extreme things happening. In the case of the SKR theory, they say that are suppressing this strong outflows are suppressing the black hole growth, and they're observing it more clearly. I think that you will be able to say it's still happening a little bit up to like this redshift, but it's suppressing the black hole growth because of the Hinton ratio match.
Yeah, the implications are very important, so
Yeah.
it's an important result.
Yeah.
Questions? I have one related to the covering factor.
Yeah.
Because in the beginning of the talk, you said that you associated the covering factor to the fact that these absorption lines didn't get to zero flux.
No, sorry. So that is a problem there. There's one thing that is called coverage fraction, that is the CF, and one thing that is covering fraction, that is the omega. So covering fraction is the angle in the sky, and coverage fraction is how you are much covering the source.
Okay. In that case,
The last one, yeah.
the covering factor.
Fraction.
Coverage, no, coverage. Is it
Yeah.
coverage?
Yeah, coverage fraction, yes.
You have the information, that information for, I guess, all the spectrum that you have analyzed as a function of redshift. Have you seen any evolution?
No. The answer is no, because I think we have explored a lot of things, and if we would have found it, it would be no. I think no. But to get a good CF, the coverage fraction, you need to really do the whole fitting study. And for the 130 cases, we haven't done it. We pick a couple of cases to do it, right? Well, we ran it over all of them, and we didn't see any numbers, but something that maybe we're gonna study more. I don't think so, but yeah. Yeah, to then see if this,
To then
Yeah.
see if there's-
yeah. We'll have to look, yeah. Thanks.
Okay. If there are no more questions, we can. Thank Paola.
And I'm here until Monday, so you can.